Alrighty, everybody. I had promised we would work out another combustion problem, and a combustion problem with excess air. So you all see how to handle that type of situation. And I'm going to go ahead and read the problem to you. It's a screenshot. I apologize. It looks like I have a grammatical error that Microsoft picked up. But we have a gas containing 50% hydrogen, 35% methane, 15% nitrogen. This gas is fed to a furnace, and it's a combustion gas. If we notice, it has hydrogen and methane. The feed rate of the gas is 1,500 cubic meters per hour. The gas is fed at a pressure of 800 millimeters of mercury at a temperature of 100 degrees centigrade or Celsius. The air is dry and fed to the furnace at a pressure of 850 millimeters of mercury and a temperature of 100 degrees Celsius. So we have two gas streams, combustion gas, which is this one, and we have some air that's fed to it to basically drive the combustion reaction. And we have different conditions. And so we have an exhaust gas now. So the exhaust leaves the furnace at a temperature of 2000 degrees C and 740 millimeters of mercury. And so we're not really dealing with STP here. There's some different conditions. And if you note, this question is pretty similar to one of the questions we went through in the last lecture. However, we're being asked to do a lot more with this problem, so these other conditions will be important in this problem. And so to ensure the complete combustion, 25% excess air is fed to the furnace. All right, so this is kind of a common process, and we've seen it with excess and limiting reactants. Sometimes you will add an excess of one of the reagents, if you will, to make sure that the reaction happens and that all of the amount of one constituent is consumed during the reaction. So you'll end up with some stuff left over. And so now we have three kind of sub questions it's asking. So we want to know what volume of air is fed at STP. And we want to know what volume of air is fed at the given conditions. And so in the last question, or last problem we had, I don't remember if it was the exact same problem as this, but it was extremely similar. We only cared about the volume of air at STP, so we only dealt with one of the conditions. What volume of air is fed to the furnace at the given conditions? So we're going to have to do some ideal gas law stuff. What is the volume of the gas leaving the furnace at the given conditions? Okay, that's important because now we're looking at some output. And what is the composition of the output gas? Of the exhaust gas, so which is really the output gas. So if we look, we have two questions dealing with input. And we have two questions dealing with output. And sometimes at first glance, these problems can be a little intimidating. I don't know if they're intimidating to you, but I remember taking these as a student and I was like, man, there's kind of a lot of stuff going on here. What really helps when you have big problems or problems that are asking for a lot of things is to simply break it down into smaller components to work with. And it's kind of the old adage, how do you eat an elephant? A little bit at a time. And thinking about it, that's a little morbid. Anyway, the first thing we want to do is probably draw a process flow chart. And I've kind of gotten away from drawing the flow chart a little bit, and I kind of alluded to, yeah, they're still kind of important, but let's focus on the chemistry. So let's draw the process flow chart. And we've kind of seen a digital version, but we'll draw, I guess, another digital version, but a handmade digital version. The system can always be, just kind of simply represented by a box. And we have two input streams this time. And our chemical equation is going to kind of govern some things. So we have some gas, and it is 15% N2. It's 50% H2, and I kind of ran out of room, so I'll put the methane above it. So 35% CH4. And a little bit of bad backkeeping, so I'm not matching the order it was given in the problem. That's all right. We have some conditions, and so it is 1,500 cubic meters per hour. And I'm noticing a kind of a boo-boo in this problem. We've not specified if it's by volume. We know if it's by volume or by mole, it's pretty much the same thing. So we're going to assume by volume, by mole for this composition. Or mole. And we've seen in previous lectures that for ideal gases, the molar composition is the same as the volumetric composition. So 1,500 cubic meters per hour, 800 millimeters of mercury. And I'm being a little sloppy. Let me, I'm sorry I'm being a little sloppy. So let me write it over here. So it's 1,500 cubic meters per hour, 800 millimeters of mercury, and 100 degrees C. And that's, I'm going to go ahead and convert to Kelvin now, 373 Kelvin. So the conversion between Celsius and Kelvin is 273 plus whatever degrees Celsius you have. So this is the conditions of our gas. We also have some air, and I'll kind of color code the air because I got a little messy, and hopefully my messiness doesn't make it confusing to everybody. But we have another stream of air, and the air is 850 millimeters of mercury. And 100 degrees C, excuse me, degrees C, not percent C. I was getting ahead because we know that air is 21% O2 and 79% N2. All right, and we're not given a volumetric flow rate because that's what we're being really to add are being asked. And I'm looking at my own grammar, and it's a little bad. It should be, what is the volumetric flow rate? But we're going to assume a basis of 1 hour later on. So that'll kind of take care of my poor writing ability, I guess. So we also have an exhaust gas, and I'll go ahead and use red for exhaust. And I should have used green all the way for our gas. So let me kind of highlight it green just to kind of make things a little more color coded. Apologize. So it's coming out hot. That's pretty hot. So 2,000 degrees C. And this was 1,000 degrees C. I apologize. 1,000 degrees C. So 1273 Kelvin. So this is going to be 2273 Kelvin. And this is, we know what it is. We just don't know how much because we're going to be asked to figure that out. So there's going to be some CO2. There's going to be some H2O, and there's going to be some N2. And this N2 here, we could say is from, well, The oxygen came from the air. So this one's from the input gas. And I'll slow down here in a second and explain it. And then we also have some O2 and N2 from the excess air. And before I said nitrogen doesn't matter, and then we'll sort of, and it sort of matters because if we're being asked for air, we kind of take into account the composition of oxygen, of nitrogen. So really we were just dividing by 0.21 when we would get our O2 value. And here nitrogen matters more because we have to keep track of it. Okay, so it's not in the reaction, but we have to keep track of it. So here N2 is not in the reaction, but we have, that's supposed to be have, I'm sorry, to keep track of it. All right, so this is a big, kind of a big deal. Maybe I'll just rainbow bright it here. Oh gosh, went off the screen, I apologize. There we go. So rainbow bright, don't know if you guys know what rainbow bright is. Anyway, we got our temperatures converted already. We have our input conditions and we have our output conditions. So input's going to equal output. We'll see that with the chemical equation. I'm going to go ahead and just write it. Input's equal to output, so all the carbon that comes in and all the hydrogen that comes in and all the nitrogen that comes in, it's going to come out. It's going to be attached to different friends. So carbon's no longer going to be attached to hydrogen, it's going to be attached to oxygen. Hydrogen's also going to be attached to oxygen. And nitrogen is not attached to anybody, it's just going to come right out. Air, so it's O2 and N2, so that oxygen is going to attach with its new friends, carbon and hydrogen. And then we have some excess air, so O2 and N2 kind of coming out. And we know the composition of that, but let's just start working through it. So A, we've kind of done A before. So what volume of air is fed to the furnace theoretically at STP? And that's kind of one thing we want to think about. Input equals output. A. So we have two reactions, and but let's figure out the amount of volume at STP first, right? So what volume is air? What volume of air is fed theoretically at STP? So to figure this out, we need, and we've done this before, we need the input gas at STP. And why do we need the input gas at STP? Well, we need to figure out how much air reacted with this input gas, and because that's what it's asking for. So at STP, so we must take the input gas to the STP conditions to figure out how much oxygen would be needed to combust it. And so what volume of air is fed to the furnace theoretically at STP? We pretty much figure it out the same way we did in the previous lecture, but we now have to account for this 25% excess air. So first, let's convert our gas to STP. And we can do that because we have our conditions here. And we can use our old friend P1 V1 over T1 equals PSTP VSTP over TSTP. And sometimes you can say 2 and then say 2 equals STP, that kind of thing for your subscript. Let's rearrange it. We want to know what VSTP is. Oops, kind of made the T gigantic. VSTP, so volume at STP, equals P1, V1, and TSTP over, can I do the simple math? There we go. T1 PSTP. Sometimes I get confused. And if you get confused with these problems, just take a deep breath, take a look at it. And it's like relax and calculate. I should make a shirt that says that. So this is equal to 800 millimeters of mercury. Our V1 was 1500 cubic meters. Our TSTP is 760. Oh wait, no, I made a mistake. It's not 760, it's 273 Kelvin. And I should be also making it in railroad track form, I'm sorry. 273 K. Got ahead of myself there, I apologize. T1 we calculated to be 373 K. PSTP, this is the 760 millimeters of, I'm going to squeeze it in, mercury. Sometimes it's hard with my digital pen here. And so Kelvin cancels. We're going to be left with cubic meters. Millimeters of mercury cancels. And you know what? Let me do the canceling in a different color. Make it a tad clearer. Kelvin cancels. Millimeters of mercury cancels. And we're left with cubic meters. And that's what we wanted. And so by my calculation, let me go ahead and work it out real time. And sorry if there's a little extra pause in this video due to my calculation activities. Times 1500 times 273 divided by 373 times 760. And I got 1155.64. So VSTP all right, so 1155.64 cubic meters is the total volume of gas. This is weird. I went from capital to lowercase. I apologize. Total volume of combustion gas. So this is the total volume of combustion gas at STP. Hooray! All right, not done yet. These problems are a little lengthy. So we have our total gas. So we need our oxygen at STP. Sorry. So now we need to figure out oxygen at STP. And so we have two reactions. We have two combustors here. We have CH4 and H2. And so we have, I'm going to rewrite it here just so I don't have to go back and forth. It's 35% CH4, 50% H2. And we know it's reacting with O2. Alrighty. So we can divide this up into two reactions. The total reaction would be CH4 plus H2 plus O2 yields CO, and let me give a little space for the coefficient later. And I want to say this ends up being 3, maybe. This is going to be comical. So we have our total reaction here, but we're going to break it into 2 reactions. Reactions, and I like to do it because to me it makes it more simpler, and it follows the old adage of breaking down the elephant. And I think this is balanced, so this is the total reaction. So reaction 1, I'll start with H2 this time. And I need to balance this right quick. And we have 2 oxygens, so 2 H2O and 2 H2. And then reaction 2 is the good old CH4 plus O2 yields and we need to balance that one kind of the same way, and it is 2 H2O. All right, so we have these 2 reactions. They're balanced, which is important, and so we need to figure out the O2 from each reaction. All right, so let me kind of highlight reaction 1, reaction 2, and we need to figure out the O2 from each reaction. So the O2 from reaction 1 and reaction 1 is dealing with the combustion of hydrogen. And our basis now, we figured it out already. This becomes our basis, is 1155.64 cubic meters. And let me highlight that. The basis is 1155.64 cubic meters of gas. Okay. And so we have 1155.64 cubic meters of gas in 1 cubic meter of gas. We have, what was the percentage? It was 0.50, so it's 50% hydrogen. We have 0.5, and I'll put 0.50 cubic meters of H2. And based on our relationship here, we could either go to moles or we could keep it in terms of volume. And we can actually keep it in terms of volume here because the ratio ends up being the same. There are two, so stoichiometry, and if I spelled it wrong, please don't beat me too badly. But by stoichiometry, from this reaction here, we have 2 cubic meters of H2 for 1 cubic meter of O2. And so that equals, let me work it out. I'm taking a Beatles song and butchering it. 1155.64 times 0.5 divided by 2 is 288.91. So I got 288.91. So from reaction 1, we got 288.91 cubic meters of O2. I didn't do the magic canceling, so cubic meters of gas canceled, cubic meters of gas canceled, cubic meters of H2 canceled, and cubic meters of H2 canceled. So we end up with 288.91 cubic meters of O2 from reaction 1. So now we need O2 from reaction 2. And reaction 2 dealt with the combustion of CH4. And so we're going to deal with this reaction here. Alrighty, CH4. And our basis is still 1155.64 cubic meters of gas. So 1155.64 cubic meters of gas. And this time we remember we had 35% CH4. So in 1 cubic meter of gas, there's 0.35 cubic meters of CH4. And the stoichiometry of this equation is telling us that there's 1 cubic meter of CH4 for 2 cubic meters of O2. So 1 cubic meter CH4 for 2 cubic meters of O2. So a little bit different than the stoichiometry up above. If you do notice, it works out brilliantly because in our total reaction, it was a 3 to 2 ratio and 3 to 1 ratio. But there are always, the coefficient for O2 is always 3. And here, this is going to be 1 O2 and this is going to be 2 O2. So even though you've broken it up into 2 reactions, if you add the coefficients together from your 2 reactions, it'll equal the coefficients in reaction 1. So everything kind of evens out. Again, it's a bookkeeping type of thing. And you can kind of check to make sure you got your 2 reactions right by comparing it to the original reaction if you so desire. And let me go ahead and calculate this out before I wander off into thought. 1155.64 times 0.35 and times 2. And I got 808.95. All right, so the total O2 from the 2 reactions equals 288 88.91 cubic meters, cubic meters of O2 plus 08.95 cubic meters of O2. Before I get too far to that side, I'm just going to write it down below. And that should be here, 288.91 plus 808.95 is 1097.86. Cubic meters of O2. Now, if you remember, we were dealing with, go back up to the problem. Man, I change scales all the time. Sorry. 25% excess. Okay, so that was a big to do. 25% excess air is fed to the furnace. And so now we want to get 25% excess. And you can add this in probably at the end. So let's figure out the amount of air. And so the amount of air so first it equals, so if we weren't dealing with excess, it would just be 1097.86 cubic meters of O2 divided by 0.21. And this equals to 5227.9. But we have 25% excess air. And so there are two ways you could do this. Okay, so two ways. To account for this. And sorry if that's account. So you could either say total air equals 5227.9 cubic meters plus 0.25 times, I'm going to use the dot as the time operator, 5227.9 meters cubed, and that'll give you the total air. Or you could just multiply 5227.9 meters cubed, multiply that times 1.25 to get for the excess air. And sometimes this one's a little bit easier. The top one is easier for students to get because this is the 25% excess, not forget to get, gosh, sorry. Or you could just multiply it by 1.25. And so if you multiply it by 1.25, it's the same as getting, man alive, my brain won't work right now. It's the same as this operator. And if you don't believe me, just work it out. So 5227.9 times 0.25 times 5227.9. Be sure the parentheses are good. Oh, plus, sorry, I messed up. 5227.9 plus 0.25 times 5227.9. And I got 6534.89. And I'm going to write it below because my scale is all off. So cubic meters of air. This kind of the simpler calculation. It's not that much simpler, but it's a little more. It's just one operator. Times 1.25 is the same, so 6534.8. I got a little bit off, but 6534.88. So it's pretty much the same. I must have rounded wrong somewhere, but it's close enough. 6534.8. Yeah, I gotta be honest and put 88. What I got. Hopefully you're working along and you can kind of see perhaps where I made my little rounding error, but it's close. So it's the same. So you can figure out the total error. So we figured out our part A, which was asking for the amount of air fed to the furnace theoretically at STP. And again, I apologize for switching scales like this, but I can zoom it and it's recorded on a video, so it's probably okay. So what volume of air is fed to the furnace at the given conditions? And so the air is dry and it's 850 millimeters of mercury and 1000 degrees C. So let's go back down. And it was 850 millimeters of mercury. So part B. So it was 850 and 1000 degrees C, which I converted to 1273 Kelvin. And we're going to figure out this volume using, again, our P1 V1 over T1 equals P2 T2 over V2. And in this case, our condition 2 is the given conditions. So condition 2 is the given conditions, which are these here. So again, we want to solve for V2. So V2 equals P1 V1 T2 over T1 P2, right? Yes, P1 T1 V2. So P1, we know it's STP. So condition 1 was STP, because that's where we calculated this volume at. The first question asked at STP. And then let me kind of highlight it. So it's air at STP. So P1 is 6534. I'm going to go ahead and use the 8, 9. It's not that much different. V1, oh my gosh, that wasn't millimeters of mercury. What am I doing? P1 is pressure. Oh, I apologize. Should edit that one out, but I won't. All right, so P1 is 760. We all make mistakes, man. 760 millimeters of mercury. And V1 is 6534.89 cubic meters. T2 is our new temperature, so 1273 K. T1 is a STP, so that's 273. And P2 is our new pressure, which is 850 millimeters of mercury. And so this is a little bit less involved than part A. And it's just an ideal gas law. So I'm going to work it out down here, work it out real time, makes it more authentic if I don't know if you can hear my calculator keys, but 6534.89 times 1273 divided by 273 times 850. And I got a kind of a big number. And almost, let me punch this numbers again. I got 232050. That's a lot of air. And it's actually per hour, if you think about it. So 232050 cubic meters of air. And let me punch this number again, just to see. 232050. Oh, I must have punched it wrong. Okay, so I apologize. Always double check. Messed that one up. I got a 27245. I don't know where I made my mistake, but so now, and I know I'm recording this, and hopefully you're not getting bored watching me check my errors, but always check your calculations and whatever you do, whether it's punching numbers, writing Python code, or whatever. Let me just give it one more time, right? Because I was only right 50% of the time when I punched my numbers in. So let me do this one more time to make myself feel a little better. 760 times 6534.89. I must have hit a decimal point wrong. Times 1273 divided by 273 times 850. And I got the same number again. So 27245.75. I had made an error. It seemed kind of big. It goes back to lecture 1 where I said always check and see if your answer made sense. And that other answer seemed really, really big to me. Anyway, so this is the answer, V2 at conditions. And I'll go ahead and highlight this part. And sorry for the little delay, but it's always good. Always go back and if you think it's goofy, re-crunch the numbers. No one's harmed by redoing your calculations. So now we have kind of the mass balancey parts. And let's go back. So we've done a lot of calculations, and again, I sincerely apologize for kind of changing the scale. I try to redistribute these, and it makes it really hard for students to read if I've changed the scale, so I made kind of a mistake there. Kind of the drawbacks, I guess, of dealing with a digital screen instead of working it out on a piece of paper. So, what is the volume of the exhaust gas leaving the furnace at the given conditions? Oh my word. Okay, so we have kind of a lot of stuff coming out, and we have a lot of stuff to account for, and so we better get to it. And so we have four constituents really. We have nitrogen coming from two places, and so this is a gas that gets pretty tricky. And so we have nitrogen coming from the gas, and we have nitrogen coming from the air. To figure out the CO2 and the H2O, we have to go back to our stoichiometric, excuse me, we have to go back to our stoichiometric relationships from our two reaction equations, because that's where our CO2 and our H2O came from. The N2 from the gas is going to be pretty straightforward. It's simply 0.15 times our entering gas. And so we have at the given conditions. So I'm going to propose this. Since we figured out our volume of our input gas at STP, and we know our air at STP, I propose that we calculate at STP first and then bring it up to the given conditions later, because it's going to be much simpler to do that. These first two, actually the first problem set the stage, or part A anyway, the first part of the problem set the stage, excuse me, tripping over my own words, set the stage for STP calculations, which it's a little bit easier because then you just use the ideal gas law to bring it up to the given conditions. So I'm going to go down and do a little bit of bookkeeping. I've said it kind of before, and I'll say it again. This class, a lot of success of this class is bookkeeping. So part C, they want volume. They want volume of the exhaust at given conditions. And so we have CO2. This is from reaction 2. We have, I'm going to do H2O, and it was reaction 1 and reaction 2. And we have CO2, that was only from reaction 2. N2, it's from the gas, and N2 from the air. And then we're going to have O2 from the excess air. And so the N2 from the air is the total air, because the N2 is never consumed. I'm specifying that the O2 came from the excess air because we're assuming that all of the anything below that 25% extra was consumed by the reactions. So it's I'm going to go ahead and put 25% excess air. So these are the four constituents and their sources. And maybe I should color code it. Yeah, that'll be easier. Sorry about that. So we'll do CO2 is green, and we'll do N2 is blue, and we'll do O2 as pink. All right, so let's start off by figuring out the H2O. And this is going to work out great because we're going to figure everything out in meters cubed. sorry for the sloppy writing, everything in cubic meters. So we're going to figure everything out in cubic meters, and cubic meters is a volume. Yay. All right. And to kind of look, we can again go back. So, I mean, I did that kind of in my head, figuring out where the sources came from. But if you look at your flow chart, it's pretty plain. And we just kind of looked at it. So CO2, H2O, we know that came from the combustion. This came from the gas. Actually, these came from the reactions. And then let me kind of label it. So I wrote it twice. From reactions. So bookkeeping, very good. We kind of rainbow brighted this. N2 is not only a reaction, but we have to keep track of it, and you have to keep track of it for part C and for part D. And we'll figure out the composition pretty easily once we do this part, which is a little bit time consuming. And again, it's all just keeping track of everything. And we've done a pretty decent job. So let me start off with H2O. Highlighter. So if we go back to reaction 1, I'm going to write reaction 1. Oh, yeah. I apologize. I'm going to rewrite reaction 1. And what did I say reaction 1 was? Hold on. There we go. So 2H2 plus O2 yields 2H2O. And our basis can be kind of whatever you want it to be. And sorry, my brain flew the coop. We went 2H2O. We can start with any of our answers, or we can start with what we said our original basis was at STP. And so we said our basis was 1155.64 cubic meters of gas. All right, so we said 1155.64 cubic meters of combustion gas. And so we can do this calculation, and you can use the amount of O2 as well. So there's kind of two ways to do it. Could also use the O2 answer you got, but let's solve it with this as the basis. So we can do 11 of gas. So this first part is kind of familiar. There was 0.5 cubic meters of H2 in 1 cubic meter of gas. And by stoichiometry, there are 2 cubic meters of H2 for every 2 cubic meters of H2O. And so this is going to cancel. So it's 1155.64 times 0.5. And I got 577.81 cubic meters of O2. I'm sorry, of H2O. That's what we were solving for. Bookkeeping, man. I would have made that mistake if I hadn't have labeled everything. So it's very, very important. Cubic meters of gas canceled, cubic meters of H2 cancels. And so we're left with cubic meters of H2O. And so from reaction one, we can kind of just work these out, and I can do kind of a sub adding later. So where else do we get H2O from? Reaction 2. And yes, there is a lot of stuff involved here, and that's why it's important to be really meticulous when you write this stuff out, because it's real easy to lose track of everything. So CH4 plus 2O2 goes to 2H2O plus CO2. Oh, CO2. I made a mistake. Hold on. Couldn't remember. My photographic memory turned off. 2H2O plus CO2. Excuse me. Knew it looked funny. All right. Right? Yes. I don't know why I'm doubting myself. It's right in front of me. Okay. Again, the same basis. And you could have also used your calculated O2, but then sometimes you might make a mistake and use the wrong one. 1155.64 cubic meters of gas. And if you remember, it was 0.35, and I should be doing 0 point for the, anyway, 0.35 cubic meters CH4 per 1 cubic meter of gas. And we're interested in H2O. And so for every cubic meter of CH4, there are 2 cubic meters of H2O. And so 1155, oops, 64 times, and that looks really sloppy. 1155.64 times 0.35. And then this time times 2. So a little bit more water coming out of here. And I got 808.95, kind of a familiar sounding number. And this is from reaction 2. So total H2O is these two added. So 577.81 plus 808.95. And so the total H2O and I got 1386.76. Let me write it nicer. let's highlight it so we can find it later. So total H2O, 1386.76 cubic meters. The next gas on our list is CO2, and that only came from reaction 2. Excuse me. And then we color coded it green. And which green? I don't know. Hopefully it was this one. Okay, CO2. Again, so it almost gets repetitive. And I apologize for that, but I can't do much about it because that's just, kind of how these problems work. And so we're going to be using the same basis. And again, you could have used the amount of O2 from reaction 2 as a basis as well. So you could use the solved O2. So there's two ways. I'm just going to kind of put this, it's kind of an aside, like a side note, but I'm going to use the same basis. The 1155.64 cubic meters of gas. And the reason I'm using it as a basis is because I've already used it as a basis so many other times. Excuse me, didn't mean to cough right in the mic. And again, this is the same reaction 2. It was 0.35 cubic meters of CH4 for 1 cubic meter of gas. And by stoichiometry, man, that was a mistake. I think it had been there the whole time. CO2, my apologies. It's a 1-to-1 ratio, so there's a 1 cubic meter CH4 per 1 cubic meter of CO2. And so this is it. There's no other source of CO2 except for reaction 2. And so it's 1155.64 times 0.35. And I got 404.47. And I just calculated it here. 404.47 cubic meters of CO2. And that's it. There's no other source of CO2. So that was a simpler calculation. So now the repetitiveness part of this problem kind of ends because we already figured out everything that had come from our reactions, okay, here and here. Now we need to find N2. So there's two sources of N2, and N2 we had, excuse me, oh, I guess it's going to be a little repetitive again, sorry. But N2 we had from, sorry, I'm losing track of my thoughts again. I'm sure that's entertaining for you, sorry. So N2 from gas and N2 from air, and from all of the air. So N2 from gas, and let me go back to my color coding. And was it this blue? I hope it was. And again, it's that same basis. It's 1155.64. And so in 1155 in 1 cubic meter, for that we go and we look at what our composition was. And so if we go back and look at the problem, and we don't have to read the problem again because we read it in our process flow chart. It was 15% N2. This has been a long problem. So the combustion gas, and I'm just going to say it was 15% N2. So there's 0.15 cubic meters of N2 and 1 cubic meter of gas. And so this is a fairly simple calculation, but you have to keep track of where it came from or else it gets kind of scary. So 1155.64, and again, this is still at STP. Okay, so we're going to have to bring it back up to our conditions to solve the problem. Times 0.15, so 173.35. And this is from gas. And so from air is a different calculation altogether. And it's nice because we already figured out how much air we have from part A. So this is the total air, 6534.88 air. So N2 from air. And it was 6533.89, right? Let me go back. My brain hurts. My brain hurts. 6534. Oops. 65. I was using the 89. It's not that much difference. Rounding error. 6534.89. So I was almost there. And so this was the answer from part A. If you remember, so 6534.89 cubic meters total air. All right, so we can multiply this times 0.79 because air is 21% O2 and 79% N2. So N2, and remember, this is the total air, right? This is the total air, including the 25% excess. Including the 25% excess. Excuse me. Sorry about that. Doing it right in the mic, I'm sure it's pleasant. Okay, so N2 from air is I should put an equal sign instead of a colon, equals 0.79. I should put 0.79 to be proper. Times 6534.89 cubic meters. .79 times 6534.89, and I got 5162.56. All right, so total N2 so the total N2 equals the 175.35 from the gas plus 5162.56 from the air. And that's including that 25% excess because we calculated it from part A, from the part A answer, or the answer for part A, excuse me. All right, so 5162.56 plus 175.35, and I got 5337.91. And I'm gonna highlight it blue. So the last constituent, so we're almost there, folks. I'm very happy. And we've color coded it so we can find our answer later. O2 from the excess air. And I used pink. I think it was this pink. All right, so how much air was excess? So total air, so first we want to calculate total air, or first we only want to calculate the excess air. And to do that, we have to go back and figure out what, and we already know what it was because we wrote it down. So if we go back up here to part A, the total air we needed was 522.97. This was the excess air. And if I was smarter, I would have calculated it and saved it for later because it came in handy later. But this whole thing is the 25% excess. So 0.25 times 522.97. So let me bring that down. So 522.97. No, that's not the... I'm writing it wrong. 5227.9. Right? I have to go back up. Excuse me, guys. Let me 5227.9. I was getting it confused. 5227.9 was air before excess. Before the 25% excess was added. All right, so the excess air was 0.25 times 5227.9 cubic meters. And so that equals 1306.98. So this is the excess air. And to get the O2, we know that 21% of this, so again, air is 21% O2, 79% N2. Air is, or O2, 0.21 0.21 times 1306.98 cubic meters. And that equals, oops, 0.21. I got 274.46. And this is from the excess. All right. So total volume is just everything now, because they want to know the total volume, and then we got to bring that up to the conditions. Woo, still a little bit of ways to go. All right, come on, didn't select my pen. So total volume is what? It is the H2O plus CO2 plus N2 plus O2, and the volume. So V, 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 V. And we know that now. So our H2O, total H2O was 1386.76. CO2 was 404.47. 404.47. N2, let's see, color coding helps. Total N2 was 5337.91. And then O2 is right in front of us, so 274.46. And we've done it in order, and that'll make part C much simpler. So 1386.76 plus 404.47 plus 5337.91 plus 274.46. So 7403.6 is what I got. And I'm going to go ahead and say that was okay. So 7403.6. And one thing you have to remember is that this was at, so this is the volume of the exhaust, okay? All right, so the volume of our exhaust is 7403.6 cubic meters at STP. They wanted to know at the given conditions what the volume was. And so it's another repetitive exercise of using the ideal gas law. So let's go back up, look at my shrunken. We were 2000 degrees centigrade, and did I forget and 740 millimeters of mercury. I'd forgotten to write a condition. So we're solving for volume, so we have temperature and pressure, which is good. And so 2000 C, 740 millimeters of mercury. There we go. So 2000 degrees C, 740 millimeters of mercury. This is going to be 2273 Kelvin. So we want to know at conditions. So the volume at conditions is, so P1 V1 over T1 again equals P2 V2 over T2. T2 is conditions, or condition 2 is conditions. Condition 1 is STP. So we want to solve for V2. V2 equals P1. I'm writing it kind of sloppily. I apologize. Let me clean it up. So P1 is 760 millimeters of mercury. What happened to my pen? It feels differently. V1 is what we solved, so 7403.6. T2 is our new temperature, so 2273 K. 2273 K. T1 is STP, so 273. And P2 is our new pressure, so 740 millimeters of mercury. And cancel, 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 cancel. We're left with cubic meters. That's what we want. So V2 equals 760 times 7403.6 times 2273. It's a big number. Divided by 273. Oops. 273 times 740. And I got 63308. All right, so if you're working along, this is what I got for this volume. It's a pretty big one too. It's 63308.43 meters cube. Hold on. That's supposed to be an @ sign. And we'll rainbow this one. It's supposed to be a rainbow. So this is part C. All right, so part D wants to know the composition of this gas. Part D, I mean, if I didn't say that. So part D, what is the composition? And to do that, it's good to use the STP calculation. So we're going to use this. Why? Because we already know what the volume of everything is at STP, and we know what the total volume is at STP. So we can do the volume fraction at STP of the exhaust. And we know it's CO2, H2O, N2, and O2. So we know that V total, we're going to use the STP. And so the STP calculation, the total was 7403.6. And I feel like I should go back and do it again, but I think it's right. 7403.6. So the V volume fraction, so Vx equals Vi over Vt. So V of your species over your total volume. So the VH2O equals, we already solved it. So H2O, if you look, we kind of worked it out almost bookkeepingly nice. 1386.76. Over 7403.6. And so that equals 1386.76 divided by 7403.6. And I got 0.19, I'm rounding. And also, yeah, I implore you to work these out along with me. Pause it if you need to. It's no biggie. So 0.19 V CO2 equals 404.47. Over 7403.6. And 404.47 divided by 7403.6. And that's 0.05. So 5%. The VN2, the V of N2, or the volume fraction of N2, is we have a lot of N2, so 5337.91. Over 7403.6 equals, so 5337.91. So it's a lot of nitrogen, so I got 72% or 0.72. And the last one is O2, so VO2. Sometimes people use this as a measure of sports capability, your VO2. 274.46, so not very much because it was just from that excess air. So 274.46. Over 7403.6. Getting sloppy. And so 274.46 divided by 7403.6, and I got roughly 4%. So 0.04. And if I add these together, they should be pretty close to 1. So 0.19 plus 0.05 plus 0.72 plus 0.04. 1. So I got exactly 1. So that's good. So it's 0.19 or 19% H2O, 5% CO2, 72%, nitrogen, and 4% oxygen. So that's the composition. So again, it took a little while, and at the beginning maybe it looked a little intimidating, and it maybe kind of was if you take a look back at everything we've done, but we did it the right way. We broke things up into little bits, and I changed my scale. It's hilarious. But we took this big problem, chopped it up into a bunch of little pieces, and were able to solve for what was being asked. And so we did some fairly decent engineering calculations. If you have any questions, feel free to email me or the TA. And good luck with these, and don't get overwhelmed. Just take it step by step, and you all will do totally awesome. And again, any questions, shoot me or the TA an email, and good luck calculating these, and hope you have an awesome day. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.